Now that we have defined what is a probability generating function, rather we have recalled, let's go and compute probability generating functions for two distributions that will be useful to solve this problem, the problem in this slide. Okay, so namely, we start with binomial distribution. For binomial distribution, the probability generating function, which is this sum, the probability of z equal to k times s power k, we just have to put in this probability, which is n choose k p power k into 1 minus p power n minus k, and then you combine this p with s so that it becomes ps power k, and then it's just a binomial sum. If you just evaluate that binomial sum, you just get this expression here, ps plus 1 minus p whole power n. The expansion of this as a binomial sum is just this thing. And this is true actually for every s in R. We only care about s within -1 to 1, but to be honest, this is true for every s in R. In particular, this power series, in fact, it's a polynomial in this case, has radius of convergence infinity. We shall use the convention binomial 0 comma p for any p strictly between 0 and 1 to be the random variable 0. And interestingly, the form of this PGF is actually going to honor this convention. Why? Because the PGF for the 0 random variable is just 1. Okay? On the other hand, so is it if you put n equal to 0 here. So therefore, we'll keep this convention whenever we have some calculations from now on. Okay. Now next example would be Z following Poisson distribution. In this case, the PGF of Z is just this sum, because this is the probability that Z takes the value k, and then we combine this lambda with s, and we take this e power minus lambda out of the sum. Now this sum is nothing but e power lambda s, so we get this thing, and then by simplifying we get e power minus lambda into 1 minus s. Again, this is a power series whose radius of convergence is actually infinity, because this is true for every s in R, but we only care about -1 to 1, so let's keep it that way. Because of the theorem that we stated and proved in the last slide, these PGFs actually uniquely determine the binomial NP and Poisson lambda distributions respectively. We'll actually use it in the calculation in the next slide. Okay, now let's back to the question, warm-up question on thinning. Now let's forget about the hen and egg story. Let's just remember that we started with an IID sequence of indicators following Bernoulli P distribution and a Poisson random variable n with parameter lambda, and also the sequence of Bernoulli random variables is independent of the Poisson random variable. Of course, this just means that if you take finitely many I1 to Ik, that vector I1 to Ik is completely independent of n. Then we defined n bar to be the random sum of the ij's from 1 to capital N. And recall that when ij was the indicator that the jth egg hatches, and n is the random variable of number of eggs given by that hen in that particular year, then n bar is the number of baby chicks born in that year. Okay, we have already gone through this. We want to compute the distribution of n bar, and what we have observed is that for any n non-negative integer, small n, conditionally on capital N equal to n, n bar follows binomial distribution with parameters n comma p. Now this is true in both when n is 0 and when n is a positive integer. Because when n is 0, when small n is 0, that is, then capital N takes the value 0, and therefore capital N bar also takes the value 0. And that's our convention for binomial 0 comma p. This is why we chose that convention. Okay? And on the other hand, when capital N takes a positive integer value small n, then obviously n bar is a sum of small n many IID Bernoulli P random variables, and hence it follows a binomial distribution with parameter n comma p. In either case, if you fix an n, rather in either case for all n, which is a non-negative integer, and for all s, which is between -1 and 1, the conditional probability generating function of n bar given n equal to n, which is this quantity here, expectation of s power n bar given n equal to n, this is nothing but the PGF of binomial NP distribution, and we have just computed it. That's because the conditional distribution is binomial NP, and that PGF has to be of this form, PS plus 1 minus P whole power n. We just computed this. So we see this, and this is true for every n, which is in the range of capital N, namely the set of all non-negative integers. Since this is true for every small n in n union 0, which is the range of capital N, we actually see that expectation of s power n bar conditional on n, this random variable actually equals ps plus 1 minus p power capital N. We have gone through this calculation a few times. Whenever you condition on n equal to n and compute the conditional expectation, you just get a number that depends on small n. But when you do this, this is a random variable, and in this case, this random variable happens to be this random variable. Obviously, this is random because n is random. Now we are in a good shape to actually compute the unconditional probability generating function of n bar, and that can be done by one more conditioning, namely, for every s in the open interval -1 to 1, the unconditional probability generating function of n bar is just expectation of s power n bar, which is obviously expectation of the conditional expectation of s power n bar conditioned on n. And this particular conditional expectation we have just computed. So let's put that inside. So this is expectation of ps plus 1 minus p whole power capital N. Now note that this is nothing but the probability generating function of capital N evaluated at ps plus 1 minus p. If you had s here, this would be expectation of s powered n, and that would be the PGF of n evaluated at s. So instead of s, we have ps plus 1 minus p, and therefore the expectation of ps plus 1 minus p whole power n is nothing but the PGF of n evaluated at ps plus 1 minus p. Now, note that n follows by Poisson with parameter lambda. And for Poisson with parameter lambda, we have already computed the PGF. And if you put that value in here, you get e power minus lambda into 1 minus whatever is here. So if you had S here, it would have been e power minus lambda into 1 minus S, according to our calculation in the previous slide. But we have this guy, so we'll have this thing. And of course, there is simplification possible because 1 and this 1 will cancel. And if you simplify and write nicely, what you would get is this is e power minus lambda p into 1 minus S. And this is true for every S in the range minus 1 to 1. And therefore, by our theorem, this should uniquely specify the distribution of n bar because this is just the expression of the PGF of Poisson distribution with parameter lambda times p. So therefore, by our theorem, n bar follows Poisson with parameter lambda times p. So PGF uniquely determines the distribution of a non-negative integer valued random variable. And in this case, n bar happens to be a non-negative integer valued random variable. And its PGF is the PGF of Poisson lambda p distribution. And therefore, n bar has to follow Poisson lambda. So what this says is that in the hen and egg question, the number of baby chicks born in that year follows a Poisson distribution with parameter lambda times p. Now, this is an example of what is called a thinning of a Poisson process, but you don't see any process yet. It is all about random variables, as I said. Now, let's go to the process level. So, we start with the homogeneous Poisson process with intensity alpha. We take a sequence of indicators, I1, I2, and so on, IID, Bernoulli P, such that this sequence is completely independent of the Poisson process NT. Again, whenever I say this, this just means if you take finitely many of these NTs, form a random vector out of it, that random vector is going to be independent of I1, I2 up to IK for every K in N. Okay? So you take finitely many from here and finitely many from here, those two random vectors are going to be independent. Define what is called the thinned process as n bar t, which is nothing but, for every t non-negative, is nothing but the sum of ij's where j runs from 1 to nt. Now, what is this quantity? Think of it this way. Suppose you have, of course, you have a original Poisson process NT, so you have arrivals, right? Arrivals of phone calls, arrival of customers, whatever it is. Suppose each arrival survives with probability P. P is strictly between 0 and 1, independently of each other, and also of the entire arrival process. Then n bar t is the process of survived arrivals. We'll see some examples, more specific examples of this in the next slide. But this is what n bar t is. So if think of the situation when all the indicators are 1. If all the indicators are 1, then this n bar t will be equal to nt. It will be just counting the number of arrivals. However, not all the ij's are going to be 1 because this is the Bernoulli P with P strictly less than 1. So therefore, this will count the number of ij's that are 1. In particular, it will count how many of these arrivals survived. So ij in this case is the indicator that the jth arrival survived. Okay, and of course, those ij's are independent of each other. That's why the survival is independent of each other. And each of them survives with probability P. That's why they follow Bernoulli P. And of course, this is also independent of the number of arrivals. That's guaranteed by this independence here. So this is completely independent. This survival is completely independent of the arrival process. This part is given by this part. And finally, n bar t is the process of survived arrivals. Now just forget about the process for a moment. Note this thing for a fixed t. If you look at it for a fixed t, you just have the hen and egg situation. You have a sequence of IID Bernoulli P random variables, and you have an independent Poisson random variable with parameter alpha times t. So therefore, this sum by the hen and egg problem, n bar t should just follow Poisson with parameter p times alpha t. The alpha t is just playing the role of lambda in the hen and egg problem. So therefore, it's not at all surprising to expect that the entire process n bar t is actually a homogeneous Poisson process with intensity p alpha. Of course, this is just proving, this is just a statement about the random variable m bar t for a fixed t. This doesn't prove that this is a Poisson process with rate p alpha. This has to be proved, and we'll do it in the next lecture with details. However, in this lecture, we'll just give 3 examples of thinning arising naturally in physics, biology, and also in arrival process situation. Okay? So here are 3 examples. The first example is coming from physics. Suppose you have a machine that produces beta particles according to a homogeneous Poisson process with rate beta per minute. If each particle is corrupt with probability QC, and QC denotes corrupt, okay, independent of each other and of the entire production process, then the useful beta particles, the beta particles that are not corrupt, okay, they form a homogeneous Poisson process. Their arrivals essentially form a homogeneous Poisson process with rate beta into 1 minus QC per minute. Now this 1 minus QC is basically the P, which is the probability of survival. So here survival means being useful. Okay. Here is an example from biology. Suppose you have a bacteria colony. The bacteria are born according to a homogeneous Poisson process with intensity alpha per second. If each bacteria dies immediately with probability PE, independent of each other and of the entire birth process, here E stands for extinction, okay? Then the surviving bacteria in the colony give rise to a homogeneous Poisson process. So the arrivals of surviving bacteria, okay, forms a homogeneous Poisson process, and the intensity of this homogeneous Poisson process is just alpha times 1 minus PE per second. Now, of course, here the P is 1 minus PE because here survival means exactly survival, not being dead. Okay. Here is another example from arrival process situation. So suppose customers arrive in a shop according to a homogeneous Poisson process with intensity alpha per hour. If each customer decides to leave the shop with probability R independently of each other and of the entire arrival process, then the customers shop in that shop according to a homogeneous Poisson process with rate alpha into 1 minus R per hour. So if you look at the process of customers who are shopping, that forms a homogeneous Poisson process with this particular rate. And of course, in this case, survival means, not leaving the shop or staying in the shop for shopping. Okay? Okay, so this is where we would like to stop today. In the next lecture, we'll give a proof of thinning result. And as we will see, it will basically verify that this n bar t has independent increments and stationary and Poissonian increments, and also it starts at 0.